Hello guys, welcome to the second session of batteries for electric vehicle. So in the previous session, we have studied about different parameters of battery and different types of battery. And we have also gone through this procedure of selecting a battery or a cell which can be used for making batteries. So we have selected a cell, we have data sheet of the cell. So further now we will go on to calculations of batteries. So in this session we will go through uh, the first topic will be it's the most basic or fundamental thing to have. After motor selection is the first step for all the calculations of batteries. So we need to have motor data and also vehicle data for calculating the battery parameters or battery calculations. So motor selection will be the first parameter. Then we will go to voltage calculations. Then I am going to introduce to you a new concept or a procedure, that is WLTP. Then we will go to capacity calculation. So how is battery capacity calculated? And then what is the configuration selected for batteries? So let's start with the video with the first objective, that is motor selection. So while selecting the motor, we do have to consider two parameters only, which are directly taken from transmission system. The first parameter is rated torque and peak torque. So these are the mechanical parameters that are required by transmission system to take the peak torque is required by the transmission system to take vehicle from a steady state to a dynamic state, and rated torque is the nominal torque that motor provides for entire durations. So these are the consideration or the filters that we use for selecting a motor. So the first, okay, here these are the parameters of motor. So take a note of it. This will be used in further slides while we do calculation for voltage and capacity. So our first term is voltage calculations. So when batteries are connected in series, their voltage add up and the capacity remains same. So this is the very fundamental thing in electronics and electrical engineering. So let's check with an example. So here are two 12-volt batteries, each of 100 Ah, and these are connected in series. In series means the negative terminal of battery 1 is connected to positive terminal of battery 2, and output is taken at both batteries end. So positive terminal from battery 1 and negative terminal from battery 2. So this makes a single series connection, and at series connection output we have sum of their voltage, that is 12 volt plus 12 volt, that is 24 volt, and the battery capacity remains same, that is 100 Ah. So I have a question for you. What if what if we connect batteries with different capacity in series? So here the batteries had 100 Ah and 100 Ah, and their equivalent capacity was also 100 Ah. So what if this was 50 Ah and the other battery was 100 Ah? What will be its equivalent battery capacity? So if you want to solve it by yourself, you can pause the video. I will be answering this question right now. So the answer of this question is, if two batteries are of different capacity, then their equivalent capacity will be the capacity of least capacitance battery. So if one battery is of 50Ah and other battery is of 100Ah, so their equivalent battery capacity will be 50Ah, because the 50Ah battery will discharge quickly or before 100Ah battery. And once the 50Ah battery is completely discharged, the series connection will break and we will get no output. So equivalent capacity of battery when two batteries are connected with different capacities is the capacity of least the capacity of battery with least capacity. So this was about series connection, how voltage add up and capacity remains same. So by taking this knowledge, we will do voltage calculation in parallel. So now you are familiar with the batteries in series, and so now let's go on to calculate voltage for our battery box. So from the previous data sheet, we know that our motor operating voltage is 36 volts to 60 volts. So motor will operate between 36 volts to 60 volts. Whereas in previous session we saw our cell has maximum cell voltage of 4.2 volts, minimum cell voltage of 2.8 volts. So there's a quick information about voltage and RPM. So voltage of battery is directly proportional to RPM of motor. Thus, if battery voltage is high, RPM of motor will be high. So let's so by this, if we want our vehicle to run at its maximum speed, so its RPM should be as high as possible. So we will consider the highest capacity of required by so voltage is directly proportional to RPM of motor. So if voltage of battery box is increased, motor RPM will increase. So for having highest RPM, for us to for our vehicle to run at its maximum speed, the battery box should have voltage which is in range of motor's operating voltage and as high as possible. So for that calculation, we know that maximum operating voltage of motor is 60 volt while maximum cell voltage is 4.2 volts. So we need to add cells in series so that we make 60 volt. So dividing 60 by 4.2, we get 14.29. So rounding it off, we get 14. So 14 cells, if we connect 14 cells in series, we get 58.8 volt. But if we connect 15 cells in series, that would have exceeded the operating range of motor. So we connect 14 cells in series, which gives us max voltage of 58.8, minimum voltage of 39.2, and nominal voltage of 50.4. So so now you can check the max voltage and minimum voltage is in the range of operating voltage. So now we have done with voltage calculation and we have number for cells in series. Now what about capacity calculation? So when batteries are connected in parallel, their charge capacity adds up while their voltage remains same. So let's check with an example. So here are two batteries, battery 1, sorry, battery 1 with 6 volt and 10 Ah, and battery 2 with 6 volt and 10 Ah. So two similar batteries are connected in parallel. You can see the positive terminal of battery 1 is connected to positive terminal of battery 2, while negative terminal of battery 1 is connected to negative terminal of battery 2, and the output is taken from, both outputs are taken from single battery. So I have a question for you. As you can see, the output or equivalent circuit of this connection is 6 volt and 20 Ah. So 10 Ah from battery 1 plus 10 Ah from battery 2 gives out 20 Ah. So what if the connected if we connect batteries with different voltage in parallel? What will be its equivalent battery voltage? So what if we connect, let's consider this battery to be 2 volts, while this battery to be 6 volt. So battery 1 is 2 volt, so it is 2 volt, 2 volt, and battery 2 is 6 volt. So what will happen? So if you want to solve this question on your own, please pause the video. I will be answering this question right now. Okay, so we all are engineers, and we know that charge always flows from higher potential to lower potential. So if we connect batteries with two different voltage in parallel, it will be a short circuit. So charge will flow from battery 2, which is at higher potential, to battery 1, which is at lower potential. As we can see, the circuit is complete. So I'll draw an electric diagram for you. So this being positive terminal. So this is 2 volt, this is 6 volt. Now you can see the circuit is complete. So if batteries are with two different voltage, so this will balance each other. So charge will flow from 6 volt to 2 volt until both batteries are balanced. So the equivalent voltage, if we connect two batteries in parallel with different voltage, will be the average of both batteries. So here for this case, the equivalent voltage will be 4 volts. Once both batteries are balanced and have equal potential or equal voltage, till that time batteries at higher potential will discharge and battery with lower potential will charge. So now you are familiar with batteries in parallel. So now let's do capacity calculation or find out the number for batteries in parallel. Before that, I like to introduce to you to a procedure, that is WLTP, which is a abbreviation of Worldwide Harmonized Light Vehicle Test Procedures. So this procedure takes data from all over the world and is combined into a graph which gives us see it gives an harmonized standard for determining the levels of pollutant, CO2 emission, fuel consumption of traditional and hybrid cars, as well as range of fully electric vehicles. So what we need to calculate from capacity calculation is fuel consumption. How much will the car consume? So that will be equal to our capacity of battery. So let's have a video describing what is WLTP.
How much fuel does a vehicle consume? Around the world, this figure has, until now, been calculated using the NEDC test. From autumn 2017, a new test cycle for measuring consumption, the WLTP, will start.
This measurement process, named Worldwide Harmonized Light-Duty Vehicles Test Procedure, represents the average daily driving behavior according to modern standards.
For the WLTP, driving data and statistical surveys from around the world were gathered. Based on this data, the WLTP has redefined specific parameters.
Most importantly, the distance to be driven and the duration of the test. The speed profile is also new, both in terms of average and maximum speeds. Based on this profile, the WLTP derives 4 specific phases: extra high, high, medium and low speeds.
Speed, duration and distance form the core of the WLTP, but it also incorporates other aspects such as driving dynamics.
These include braking actions, stop times and acceleration phases. Even rolling and air resistance, as well as all available engine gearbox combinations, are considered.
Optional equipment also affects the weight of a vehicle.
So the WLTP also takes into account any of these.
To ensure that consumption measurements are comparable, the test conditions have to be replicable.
For this reason, the measurements take place on a dynamometer according to international standards. Here, day-to-day driving is simulated and the average consumption is calculated for every model and every variant anywhere in the world.
With the WLTP, consumption figures come out higher than before.
Because this procedure shows more realistically how much a vehicle really consumes in daily driving.
The WLTP, starting in autumn 2017.
So that was all about WLTP. So you must have been familiar with how the data from entire world is calculated, collected, and we now have a procedure to calculate the fuel consumption rate of a vehicle, a lightweight vehicle. So according to WLTP, let's read it. Capacity of battery pack was calculated as per WLTP process. So as per this cycle, lightweight vehicles are classified in 3 categories as per their power to mass ratio, and it is as follows. So 3 classes are divided: class 3, class 2, class 1, according to power to mass ratio, that is PMR. So taking the situation for a vehicle, the max power of motor, as we saw on the first slide, was 4.2 kilowatt, while the grub mass of vehicle is 180 kgs, that is without driver, and it goes equal to 0.18 tons. So therefore, calculating the PMR, we get it around to be 2.33 kilowatt per ton, as PMR is greater than 22. So the vehicle belongs to class 2 of WLTC cycle. So our vehicle, the vehicle for which the battery calculations are done, belongs to second class. So for class 2, we have this graph for all classes: class 1, class 2 and class 3. So according to this graph, we get the distance covered by a vehicle in 4 different sections, that are low, medium, high and extra high. So for second class 2 vehicle, the in time duration in time duration 0.5 hours, that is 30 minutes, distance covered will be 649 kilometers. So now let's calculate the energy consumption per kilometer. We know that energy is equal to power into time. So we have a motor with rated power 3 kilowatt, and we know the uh, cycles are considered for half hour. So time equal to zero point 0.5 hours. So calculating the energy, we get it 1.5 kilowatt hour. That is equal to, sorry, mistake here. It should be watt hour. So it's equal to 1500 kilowatt hour. Sorry, 1500 watt hour. Therefore, energy per kilometer is equal to 1500 upon 22.649 watt hour per kilometer. That is equal to, so let's name this term as EP, energy per kilometer. That is equal to 66.228 watt hour per kilometer. So take this term. So the average speed of our vehicle is was calculated by transmission system and was about 50 kilometer per hour. And the event that we participate in, that is ISI's ESVC, has an endurance event of 1.5 hours. This is the event where our actual battery capacity is tested. We will do all the battery capacity calculations according to endurance event. So our endurance event is of 1.5 hours. Thus, range of vehicle will be average distance in 1.5 hours. That will be equal to speed of vehicle into time. So by multiplying 50 with 1.5, we get 75 kilometers. So now we have range of vehicle. So we have EP, that is energy per kilometer, and now we have range of vehicle, that is 75 kilometers. So the next term is average energy. So average energy is equal to EP, which is energy per kilometer into 2 minus eta, where eta is efficiency of motor. So efficiency of motor is electrical to mechanical power conversion rate. So according to data sheet, the motor has efficiency of 90% or efficiency equal to 0.9. So putting value of eta in the formula, we get average energy equal to 72.85 watt hour per kilometer. So we know that energy is equal to capacity upon work done. Thus, capacity is equal to energy into work done or the distance. So capacity is equal to energy into distance, which is equal to 72.85 into 75. So we have the data calculated before. Thus we get battery capacity equal to 5.463 kilowatt. Now nominal voltage of battery is 50.89, which was calculated in voltage calculations. Thus batteries AH, that is batteries charge capacity, is equal to watt hour upon voltage, which is 5.463 kilowatt hour, it should be hour, kilowatt hour upon voltage, that is 50.89, which gives to be 107.365 Ah. So by calculation from WLTP, we have our minimum requirement of battery capacity, that is 107 Ah. The required capacity of battery 107.365 Ah, and the cell that we have selected has its maximum capacity at a certain operation equal to 3.5 Ah, which is the max capacity of cell. So thus dividing 107 by 3.5 we get 30.6. So truncating that number to a whole number we consider 30. Thus if we connect 30 cells in parallel, we get a battery capacity of 105 Ah. So now we have our parallel connection also. Thus our configuration of battery box is complete. Thus from voltage calculation we have the series connection, which is 14S, and from the capacity calculation we have the parallel connection, which is 30P. Thus our battery has a configuration of 14S 30P. So that was all for today's lecture. So objectives completed in this lecture were motor selection, voltage calculation. We got familiar with the process of WLTP, which is uh, initialized in 2017 and now used worldwide. Then using WLTP process, we did capacity calculation for our battery box, and once we had voltage and capacity calculation, the battery configuration was decided. So thanks for watching. This was all for today's session. We will meet you in the next session. Thank you.